Hello everyone. Today we are stepping into the world of the greatest integer function. We will simply touch one corner of the world of the greatest integer function in this video. And this greatest integer function is also known as the floor function. And yes, it is called the floor function because there is a reason behind it, I believe. This function brings down literally every number to the earth. Okay, so I have two solutions for the question you see on your screen right now. And as usual, the first solution will be quite analytical. We will bravely face the definition of the greatest integer function in each step and build up the solution logically and find out the number of solutions what we required. In the second solution, we will go graphical. We will look at how to find the number of solutions by just plotting the graphs of the functions involved in this equation. Not just one graphical solution, we will do two graphical solutions. So we'll see it. And as a bonus, towards the end of this video, we will dive into the GeoGebra to explore the fullest behavior of the functions involved in this equation. And in this process, you will also learn how to draw the graph of the floor function in GeoGebra. So let's get to the floor. Alright, so we are here and we have this equation. Let me write this equation again. So x cubed minus the floor function of x plus 1 is equal to 4. And you know the property of a floor function is if I have this greatest integer of x plus I can write the greatest integer of x plus I, because this is an integer, we can take it out. In this way, we can just simplify this equation in this way. This will become minus 1 and I can throw it on that side, so that will become 5. We can make it more simpler. I can write the greatest integer in one side and I will bring everything on the right hand side. So I can write this way, the greatest integer is equal to x cubed minus 5. And now I'm breaking it down by the definition one by one and see in which interval the solution will fall. So I'm taking the first interval, let us say for box x equal to 0, it means I can say x must lie between 0 and 1. So the hope is that we will find the solution between 0 and 1. And we are setting the reference side to 0 and confirming an equation of cubic to solve. So I'll get it what? X cubed minus 5 is equal to 0. We can also write in this way so that always right hand side I have to substitute something. But anyway, x cubed minus 5 is equal to 0, and that will give you x cubed is equal to 5. And so x is equal to 5 to the power 1 by 3. Now this 5 to the power 1 by 3 cannot be a number which lies between 0 and 1. Because whatever number you take between 0 and 1, you cube it, or maybe doesn't matter how many times you are taking the power or how many times you are multiplying it again and again, it will be always lesser than 1. And by any chance, this 5 to the power 1 by 3 is not lesser than 1. So this is not our required solution. So this fails actually. So we'll call it like this. Now we set to the other integer. So the next integer I will set it 1, and I have x from 1 to 2. In this way, I am getting this x cubed minus 5 is equal to 1. And so it will turn into x cubed is equal to 6. And I have x equals to 6 to the power 1 by 3. Now we have to analyze cleverly that whether this value x to the power 6 x is equal to 6 to the power 1 by 3 is lying in this interval or not. So how do we analyze it? This thing we have to analyze. So how do we analyze? Let's see it. We knew that 1 to the power 1 by 3 is 1 only. And also we know that 8 to the power 1 by 3 is 2. Of course, I can say that this 6 to the power 1 by 3 is lesser than 8 to the power 1 by 3, but greater than 1 to the power 1 by 3. But just leave this left between the middle term, but you can just write the left hand side as 1 and this 6 to the power 1 by 3, and this will become 2. So automatically we see that this 6 to the power 1 by 3 fall in this interval. So this 6 to the power 1 by 3 our correct choice, and this one solution we got. We had to find the number of solutions, all solutions. So 6 to the power 1 by 3 is one solution. We are also to find the integral solution. We'll see it later. But let's first fix on this. Now we go for the third integer, box x equal to 2. It means we are looking for the number x lying between 2 and 3, and this will turn into x cube minus 5 is equal to 2. And so I have x cube is equal to 7. So x equals to 7 to the power 1 by 3. By the same logic you apply, this 8 to the power 1 by 3 is still greater than 7 to the power 1 by 3. So it will fall between 1 and 2. But in this case, I need a number between 2 and 3. So of course, this will not be our solution again. One more time we will see, and we will identify the pattern, whether it is following or not. So let's say box x equals to 3. It means we are looking for the number lying between 3 and 4. And so x cube minus 5 will be equal to 3. So I have x cube is equal to 8. And so x equals to 2. When x equals to 2, I have a very nice number, integer. So many students can say, oh, we got the integer solution here. But you think this x equals to 2 is again not lying in this interval. X equal to 2 is not in this interval. You see that? Therefore, x equals to 2 is also not our required solution. So what will happen? What is the consequence of this kind of pattern we observed? It's easy to now infer something. Let's do one more and then we will infer it. If I have box equals to 4, x will lie from 4 to 5, and so I have x cube minus 5 is equal to 4. This will turn into x cube is equal to 9. So x equals to 9 to the power 1 by 3. Now notice 9 to the power 1 by 3 is certainly greater than 8 to the power 1 by 3, that is greater than 2. But still it's less than 10 to the power 1 by 3. Correct? It's less than 10 to the power 1 by 3. But what is happening? This number is very moving very slowly. But the integer thing is rapidly moving rapidly actually. So what is happening? That 10 to the power 1 by 3 is a number I need. This is actually a number which will be multiplied 3 times to get 10. Isn't so? This is the meaning of 10 to the power 1 by 3. I need a number k which will multiply k times k times k. Then we'll get 10. But you think this is a number 2 we multiply to get 3 times to get 8. But after 2 integer is 3. If you multiply 3, you will get 27. It means this is not by any chance 27. So that number what we are looking for must be lesser than 3. Because at 2, the cube you are getting 8. Means for 2 cube you are getting 8. So 8 to the power 1 by 3 is 2 exactly. So 10 to the power 1 by 3 by any chance cannot be more than 27. It must be less than 27 because I need a number which could be multiplied 3 times to get 10. I hope you understood. I am repeating the same thing again and again. So see here, That number is less than 10, but I need a number which is lying between 4 and 5. So this is also not our required solution. And what will happen after this if you set 5 again? So this will move very rapidly, and the value what you find for x will be very slow goer. So we cannot meet that thing, and they will never find the solution again. So this is the story for the x greater than 0 or equal to 0, means greater than equal to 0. We found that there is only one solution. We found that x equal to 6 to the power 1 by 3. Can we get any solution which is less than 0? So for less than 0, let's check one thing. Suppose I'm taking x lies between -1 to 0. The first integer I'm taking from the left, to the left. So I have, this will give you box x is equal to -1, and I'm looking for the solution here, and I have x cube minus 5 is equal to -1. Yes or no? Because the box will be -1, and they'll give you x cube is equal to 4. So you see, the solution what we are looking for here is always negative, but I'm getting here positive. So in negative part, by any chance you cannot get any solution, because every time you put a negative number, it will make it positive. And of course, after some time, you may get negative, but it will not match up the solution, this interval. So therefore, there is only one solution we got for non-integer. So the number of all solutions is only 1. What is the number of integral solution? Since we got the integral solution not so far, and basically I should solve this first part by seeing whether solution integral is possible or not. So let's also find out whether the number of integral solutions is possible or not. So let's see. Suppose we have x is an integer. Or let's say x is equal to integer. Y belongs to integer. X is equal to an integer. It means I can safely substitute this x in the original equation here. X cube minus box x is equal to 5. And so I'm getting the n cubed minus n, because now the integer of n is n only, is equal to 5. By any chance, if I can get an integer solution for this equation, I am sure that the integer solutions of the original equation we have. So can you tell any number of such a structure to get 5? By the way, let's say more deeper, n plus 1 and n minus 1. If you do in this way, you can think there are 3 consecutive numbers. Now tell me, by any chance 3 consecutive numbers give you an integer? Not integer, it's 5. Because if you take any 3 consecutive integers, between them one even automatically will come, and it will give you the entire product even number. Even two consecutive you also take, you get even only. And so this 5 cannot come. So no integer solution is there. So the number of total solutions, we can say what we found here is x to the power x is equal to 6 to the power 1 by 3. So their total number of solutions is 1 only, and number of integral solution is 0. Now all the solutions, so there's only one solution. Why all the solutions? All the solutions lie between 0 and 2, between 3 and 4. So of course between 3 and 4 not possible, between -4 and -3 is not possible, between -2 and 0 not possible. So it is given 0 and 2, but of course the number, it is actually precisely lying between 1 and 2. But do you not think that is also lying between 0 and 2? Yes, it is lying between 0 and 2. So the correct answer is A. Alright, so this was the solution analytically I have done. Let us do the same question graphically. In this graphical solution, I want to find, not find actually, yes, we have to find the number of solutions. So I want to draw the graph of the fx is equal to x cube minus 5 and I will compare with the graph of box x, that is gx. So on the same plot, I will draw the graph of x cube minus 5 and the greatest integer of x, and we will see how many times they are intersecting each other. This is the graphical way to think, one way. So for that, let me convert everything into the grid so that it will be easy to see where are the numbers. So first we draw the graph of greatest integer here, and we see this is the graph of greatest integer from 0 to 1, then 1 to 2, then 2 to 3, then 3 to 4, then 4 to 5, and then 5 to 6. So this is 1, 2, 3, 4, and 5. And this is the a graph of gx I have drawn, that is the box x. And here also we can draw it, no problem. That is, this one, then this, then this, and then this. So this is the graph we have drawn for gx. Now we are intended to draw the graph of x cube minus 5. So for x cube minus 5, how do we draw it? Let's see. So for that, I have to drop the graph of x cube 5 units below the x-axis, isn't it? So the graph of x cube I have here, and I have to shift it 5 units down. So 5 units down, 1, 2, 3, 4, 5. So graph will start 1, 2, 3, 4, 5. So it will start like this, and it will never intersect this any branch, because now this will go this side, this side, this side. It will never come. So you can see that in negative part, I have no intersection of these two graphs. Now to find out this graph accurately or close to accurately, we will find the value of this function at integers. Let us find how. When I put x equals to 1, that will give you minus 4. So I must have 1, 2, 3, 1, 2, 3, 4. So at minus 1, it should be minus 4. So it will go like this. And you notice at 2, it is going to be at 3. Because when you put x equal to 2 there, it will become 8 minus 5, that is 3. So at 2, it is somewhere here. So how it will pass like that? Of course, I have to cross this, because at 1, now it cannot turn it this side. And at 2, it has to be at this guy. So what will happen? It has to cross somewhere like this. And at 2, it cannot cross this point actually. Otherwise, at 2, the value would be 5. So it has to cross like this. And without touching this part, it will hit this point. And in this process, you can see that it will only touching the greatest integer in only one point, which is lying between 1 and 2. And that is why we got that solution 6 to the power 1 by 3 between 1 and 2. So this is the one way to draw the graph. The second way is we can draw it by taking fx something else and gx something else. So I'm again taking this thing separately, and I'm conveying what I want to say. So let me just copy it, and here I have this function. So what I'm saying that in this situation, I'm just trying to write x cube minus box x graph, and we'll compare with 5. Now I'm thinking I have one graph that is gx, x cube minus box x, and the other graph or the line y is equal to 5. I'm comparing these two. And how we can draw the graph of x cube minus greatest integer. So there is a technique here. So how do we draw it technically? Let's see. First, draw the graph of x cube. So I'm drawing this graph of x cube here. Drawing this part. Okay. So you understand this thing. So what is the point? So I'm saying that between 0 and 1, if you are taking, the box x will become 0. So the function gx between 0 and 1, I have to plot only x cube. So if I have only x cube, I'm just taking this branch, only that part. And at 1, this is a blank, so I will just take it blank. Now between 1 and 2, the gx function will become x cube minus 1. It means I have already drawn the graph of this x cube function. I have to drop it, the same graph, drop it 1 unit down, and that portion I have to take it between 1 and 2. So you can see that between 1 and 2, I have this whole entire portion. So what I can do, I have to drop it 1 unit down. It means now this will start from here, and this is stopped at 8. So now the graph I'm looking for will stop at 7. So at 2, you can see that it will become 7. So it will stop here, and the graph will look like this. Correct. And after that, this part of the graph, what I'm going to erase in dashed, so that you can understand what I want to say. This part is not anymore in this. So we are drawing this black graph or blue graph, what you can see on the screen. That is only the graph we are considering. After that, again, the red graph would be from 2 to 3, that is, will go to 8 to 27. And that branch we have to bring. So suppose I'm taking x 2 to 3, that will gx will come out to be x cubed minus 2. So this 2 to 3, the branch after that, we have to shift 2 unit down. It means this graph was at 2, it was 8. So now it will come at 6. So it should start from here at 6. So 7 is there. So this is actually my drawing is, the human drawing is not that much accurate. That's why we'll use the tool, and you can see this will be there, and from there again we'll start and so on. But our work is already over. You can see what will happen, that I have to draw the line, and line is what? Y is equal to 5, and y is equal to 5 is a line 5 unit above the x-axis. So 1, 2, 3, 4, 5. So we are drawing the line here. It is intersecting only this portion of this graph, and is intersecting the portion which we drew or which we have drawn between 1 and 2. Therefore, only one solution. After that, this line has no interaction with any branch of this x cube minus any integer if you draw, because everything will draw after that. It will be always above the y is equal to 5 line. That's why there's one solution here only. Alright, so this was the solution I tried to convey you graphically by human hand. So there is a chance of non-accuracy, and always there is a chance of mistake if you don't understand and analyze correctly to draw the graph. But let's understand this whole thing in GeoGebra, and we'll plot these two graphs together in one plot, and we'll see how these two graphs are giving the same solution. And in this pursuit, you will also learn how to use the GeoGebra to plot the graph of floor function. So let's dive into GeoGebra. Alright, so we are in GeoGebra now, and I have to plot the graph of x cube minus 5 and box x. So to plot the graph of greatest integer function, the GeoGebra has no such facility to write greatest integer function. So plot it, I have to write floor. So floor, and you can see there is a drop down, and you can hit it, and you have to put x there. So you can see that this is the floor function they have drawn. But there's one drawback in the GeoGebra. They will not show that this one is not taken. There's no such blank circle what we usually draw in hand. But anyway, we have to understand this thing. So this is our greatest integer. Now I'm plotting by taking gx as another function, that is x cube minus 5, and you can see that this is hitting this greatest integer in only one point, that is between 1 and 2. Okay, so this was the I think first solution we tried by just taking these graphs. The second solution we also tried by plotting x cube minus box x and y is equal to 5. So for that, let's disable these two and let's start afresh, and I'm trying to draw the x cube minus box x. So I'm taking a new function hx, and that I'm calling x cubed and minus the floor x. So you can see that the floor x you have already drawn fx. You defined actually the floor x as fx. So there's one facility we have that we can simply write here, type here f, and you can see that the floor function is drawn for you. So this floor function is drawn. You can see if you zoom in now, zoom in, you can get that idea, the same or similar graph we have also drawn. And the right hand side of this second solution, we drew y is equal to 5. So this is simple. We can simply write y is equal to 5. It will give you this horizontal line 5 units above the x-axis. And to see more vividly, we can change the color of this. So for that, I have to go there, or maybe right click there on this dots. No, not at all. So I have to click this thing, or maybe go to setting, then color we have to choose, or let's choose the color, this one. And we saw that now the similar thing what we observe, this graph is happening. So you can see that when I do this graph here between this line, I overlapped this line, actually line x equal to 2, so that's why you're not that much sensible. But now in this tools, any mathematical graphical tool, you can see every graph clearly and understand how the functions are behaving. So I hope you understood everything and you will apply all the techniques what you learned in your problem solving. And you can also explore GeoGebra, it's already free. So I know that this question was not that much difficult for many students, and this video was only meant for the beginners. I will take up some more difficult questions in upcoming videos. So stay tuned and stay math active.